Hello Legacy students, today we're going to look at imaginary and complex numbers. What you're going to want to have on you, your own notes, pen or pencil, and then also a calculator. Your learning objective, I can work with imaginary and complex numbers. So, once upon a time, a man sat down to solve a quadratic equation. Well, he subtracted 10 from both sides, like you would do. And he did x squared equals the square root of negative 10, and then he square root of both sides. Well, he tried that, and that didn't work. And he didn't like what he saw. There was no solution, and he knew there were supposed to be two solutions. So, what can you do? So what Rene Descartes did is he decided that even though his calculator didn't understand negative square roots, he developed a plan. He invented a new sort of number system that gives new types of numbers. And so the imaginary number system was born. So here's what imaginary numbers are. I equals the square root of negative 1. So I is for imaginary. So basically, if you have a negative 1 under a square root, you can translate that to I. So I squared then is technically negative 1. Now, how do you use I to rewrite square roots? So if I have the square root of negative 25, I can rewrite this as the square root of negative 1 times the square root of 25, right? Because negative 1 times 25 gives me negative 25. Well, the square root of negative 1, well, that's just I, right? Because we learned that before here. 25, the square root of 25 is just 5. So I can rewrite this as 5i. Now, it's customary to put the number before your I just so you see it, kind of like we do at 5x. So we'll do it as 5i as well. What about the square root of negative 6? Well, same thing. We need to take out a negative 1, multiply that by a square root of 6. Well, square root of negative 1, well, that's just I. And then square root of 6 doesn't simplify down at all, so I can just leave that as I square roots of 6. Let's try it again. So I got the square root of 40, so let's break that down. Got negative 1 and the square root of 40. Now, square root of 40, I think that guy can come down, which I think a 4 and a 10 can go in there, right? Well, square root of 4, well, we know that to be 2. So, and this is I right here. So I'll rewrite this. I have 2i and then square root of 10. So 2 times I times the square root of 10 is equal to the square root of negative 40. Let's try it again. So 5 square roots of negative 48. So the very first thing I know is I'm going to take out an I, right, to get rid of that square root. Like that. Now 48. What numbers can go into 48? 16 I think can. So 16 and 3. Square root of 16, well, that's 4. So I can rewrite this as 5i times 4 square roots of 3. Let's simplify this down even further, because this is multiplied. So 5 times 4, well, that's just 20. So I have 20i square roots of 3. Same thing. Let's try this. Just like before, we can break that into two little square roots, top and bottom. Let's get rid of that I in the inside on the top there. So I'll get I square roots of 10 square root of 3. Can't leave it as the square root of 3. Remember, got to rationalize our denominator. So I'm going to multiply by the square root of 3 on the top and the bottom. So I'm going to get I square roots of 30 all over square root of 9, which is 3. And that's my final answer for that particular problem. Because the square root of 30, 4 doesn't go in, 16, 25. None of the perfect squares go underneath it. So I can just leave it as that. Now, how do you simplify complex numbers? You're going to want to write it as part real, part imaginary. So you're going to want to write the number first and then the part with the I second. So this one, I have I times quantity 3 plus I. So basically what you want to do is distribute that I in. So I'll get 3i here plus I times I, which is I squared. Don't stop. Don't wait, though. Wait. I squared. That is... Well, technically, isn't this the square root of -1 squared? Right? Because I is the square root of -1. Well, squared, square root cancel out, so I'm left with 3i plus a -1. Which, if I want to write the real part first, I'm going to write -1, right? So I'm going to get -1 plus 3i for my answer for this particular one. Whenever you see an I squared, you're always going to want to rewrite that. Now, this one I have 3 plus 2i plus 4 minus 6i. So basically, we're going to combine like terms. 3 and 4. 3 plus 4, well, that's just 7. 2i and -6i, well, that's -4i. I'm done with that problem. I combined my like terms that are with each other. So the I guys went together and the real part went together. Let's do some distributing on this one. So I got 3i times 4, so that's 12i. Little mess up right there. 3i times -5i is going to give me -15i squared, because I had 2 i's, right? What else can I multiply by? 6 times 4, that's a positive 24. And 6 times -5i is -30i. Now, let's combine some like terms. So I got 12i and -30i. Well, I know that's -18i, right? 15i squared plus 24. Well, I squared, that's the same as -1. So technically, I have -15 times -1 right here. So basically, I'm going to get a positive 15. So I'll have -18i plus 15 plus 24. So if I write this as the real part, or the numbers together first, and then the I part, so 15 plus 24, that is 39. And I'm going to put the I part second here. Done with that particular problem. So basically, watch out, distribute to everybody, multiply everybody out. I squared is the same as -1, and then combine your like terms. Now, let's look at when we are dividing by an imaginary number. When you divide by an imaginary number, what you're going to want to make sure you do is get the imaginary out of the basement. So you can't have it in the denominator. How are you going to get it out of the denominator, you're probably asking. What you're going to do is multiply by what's known as the complex conjugate. You're probably saying, what does that mean? Well, what it means is you're going to multiply by the same thing, but the sign in the middle is going to change. So, I have 3 divided by 2 plus I. What I need to do is I'm going to multiply by this thing, except it's going to be a negative. So I'm going to go 2 minus I. Because technically, I'm just multiplying by 1, which is fine. I'm multiplying by itself. So, if I get this, let's multiply the top. So I'll get 3 times 2 negative I, so that's 3 times 2, which is 6, and 3 times -I, which is -3i. Let's multiply the bottom now. I gotta write this off to the side so I can see it. There we go. So 2 times 2 is 4. 2 times -I is -2i. I times 2 is 2i, and I times -I is -I squared. You're probably saying, I still have i's on the bottom. You don't actually, though. Look, these guys have canceled out. -2i plus 2i, it's gone. So I'm left with 4 minus I squared. I squared, though, is -1 in disguise. So I can rewrite this as 4, and it's a -1, which is positive, right? So 4 plus 1. So my answer, 6 minus 3i, all over 5. Let's try one more. So I got 3 plus 2i over I minus 4. I have to get that I minus 4. Gotta get rid of it. So I'm going to multiply by the complex conjugate, which is I plus 4 on the top and the bottom. So, bottom here, we're going to get I squared. Now, would you agree with me that I'm going to get positive 4i and negative 4i, which is going to cancel each other out? So I'm going to be left with negative 16. Well, I squared, we know that's negative 1. So I know the bottom here is going to be negative 17, right? Because negative 1 minus 16 is negative 17. Let's multiply the two numerators here. So I got 3 times I, which is 3i. 3 times 4, which is 12. 2i times I is, whoa, I don't know what I was trying to write there. Hand went a little crazy. 2i squared, and 2i times 4 is 8i. Let's combine our like terms. So I got 8i and 3i, so I know I have 11i. And 2i squared. Well, I squared, remember, that's just negative 1. So I have 2 times negative 1 right there, right? Which is negative 2. And I have 12 minus 2, which is 10. But remember, you always want the real in front of the imaginary. So I'm going to go 10 plus 11i all over negative 17. And that will be the final answer. And that's the end of this video. See you later, Sabers.